everyone. I'd like to welcome you to our first webinar of a series of 2 webinars about water in the West. Today we're going to be talking about challenges of the Colorado River Basin with a panel of 2 experts. And we asked you to fill out a poll in the survey that's going to be posted very soon, so watch the chat window. We want to find out where, if you are in the Colorado River Basin located, or if you are from outside the Colorado River Basin. So it's posted, the poll is posted on the website now. We have 75 people registered today. We have a lot of teachers participating. We have over 50% of teachers. We have about 20% other educators, 11% interested citizens, and about 14% of scientists. So we have the entire spectrum of people interested in this topic about the Colorado River. I would like to start introducing just briefly the 2 facilitators. That's myself, Anna Gold, and Deb Morrison. She's on the chat window. Then we have in the background 2 other people doing the technical support. This webinar is brought to you by Learn More About Climate from the University of Colorado here in Boulder. It's supported by Ceres and also by funding from NASA and the NASA NICE grant. Quickly, a few details about the structure of this webinar series. So it's called a series because we have 2 webinars in this Water in the West. There's going to be another series coming in the future, in the spring. We will talk about extreme weather events. This was all born out of other professional development we've been doing for teachers and educators and people. We've usually just done Climate 101 courses, and educators have always asked, how can we learn more? How can we drill in deeper? So that's what we are doing here now. We are drilling in more into water issues in these 2 webinars. And today we are talking about a very, water in the West and the challenges of the Colorado River. We have a website with a lot of background materials. So we will always refer to this. This is really only to give you a framework. And the website, the link is on the in the chat box, so you can see all the background readings there. We offer this webinar or this series for credit for teachers that are interested. Again, see the website, the link in the website for more details. If you are taking it for credit, we will ask you to participate in both webinars and then do some curriculum development. We'll work with you individually, and we're hoping that you can that you can take one of the topics that are discussed either this time or next time and develop some unit and implement the unit in your classes. There is going to be another webinar series in the spring, so stay tuned for more details. And with that, I would like to start this panel. The format is that we have these 2 panelists that they're going to introduce themselves shortly. We will have prompting questions. They will tell you their story about the Colorado River Basin. And there will be, after each question, there will be questions from the chat window posted. So if you have a question, please post it in the chat. We are monitoring it, and we're going to address it at the end of each of the sections. If you have ideas of materials that you're using in your classroom, or if you are a policymaker, some cool data, or if you're a scientist and know of resources that can be of use to others, please post them also in the chat, and we'll monitor this and make it available to others. So with that, I'd like to ask Doug to introduce yourself.
Sure. I'm Doug Kinney. I'm the director of the Western Water Policy Program here at the University of Colorado.
And I'm Jeff Lucas, Senior Research Associate with the Western Water Assessment Program here at the University of Colorado.
All right. So let's start. Where is the Colorado River shed? Is it in Colorado? Where does the river flow?
Right. So the map you're seeing now is showing the major rivers of the United States, and the width of the blue line is proportional to the average natural flow in the river. And so we've got the Colorado River Basin highlighted in blue in the lower left of your screen, and you can see it's the biggest river in a very dry part of the country. It does not stand out relative to the big rivers of the eastern United States or the Pacific Northwest, except in terms of length, but it's a very important river for this relatively dry region. And zooming in to the Colorado River Basin itself, it's a long river, 1,400 miles long, extending from headwaters in the high mountains of Colorado, Wyoming, Utah, New Mexico. When it leaves those headwaters, it is traveling through very arid country in western Colorado, Utah, and famously the Grand Canyon in Arizona, and down along the Nevada, Arizona and California border, and shortly into Mexico and into the Gulf of California. And it covers about 250,000 square miles. That's about 1/12 of the lower 48 states.
Yeah. Jeff showed you a few maps here that are the physical features of the river. Let me talk a little bit about the human imprint on this river. As you can see, it covers parts of 7 states and 2 countries. And you may, if you're very astute here, you may notice that when the maps the scientists use typically show the basin extending into Mexico, and the maps that the policy people use typically don't show the basin extending into Mexico. I'll let you guess about the politics there, but it does extend into Mexico, and it also covers part of 22 Indian reservations. It's a water supply for 40 million people. Now, it's not the exclusive supply for 40 million people, but at least 40 million people use the water to some degree. Irrigates over 5 million acres of land, and that's, again, in a very arid region, that's a very significant contribution. There's quite a bit of hydropower generated at Hoover Dam and Glen Canyon Dam specifically, and it's home to 11 national parks, countless other wildlife refuges, and so on. Most of the basin is actually federal public land. Another map, and again, another map that likes to pretend that Mexico is not part of this basin, but it is in fact. The reason I'm showing you this map is because one of the interesting features of this basin is that most of the users of the water are actually outside of the basin. And if you want to look in a clockwise direction here of all the cities that are outside of this, that use Colorado River water but are outside of the basin, you can go from Cheyenne, Wyoming, to the cities of Colorado's Front Range, including Denver and Boulder, into New Mexico, Albuquerque, then swing back around to get to Southern California. This is an important water supply source for the whole Los Angeles, San Diego region, and even up to central Utah, the Salt Lake region. The other big cities that use this river are in fact in the basin, notably Phoenix and Las Vegas. So it's a little interesting that you have these important population centers outside of the basin, because when it comes to a phenomenon such as drought, if you live in Southern California, what you're worried about is not so much a drought in Southern California, but a drought in Colorado, because that's where this basin originates. So let me pass this back to Jeff.
So getting back to the physical context of the Colorado River Basin, if we look first at the spatial patterns of where the water comes from, returning to those mountain headwaters, primarily in Utah, Wyoming, and Colorado, we look at the map on the left. It shows the average annual precipitation over the last 30 years. And the green and blue areas are showing those areas with at least 30 inches of precipitation, and those are those high mountain headwaters. And then the orange areas show the more arid parts of the basin. And if we look on the right, where is the runoff coming from? Well, from those mountain headwaters, and what you should see is that the scale goes quickly down to zero, those orange and red shades over the map on the right show that most of the Colorado River Basin's land area does not contribute any runoff to the river itself. That it's actually a very small proportion of the land, those high mountains above 8,000 feet, that are doing most of the work in generating the runoff. And because those are high and cool areas, the precipitation is mostly falling as snow, and that has an important implication for the timing of the runoff, when the water is actually available in the river to either use directly from the river or store in reservoirs. And this is what we call snowmelt-dominated hydrology, where the snow is falling from about this time of year, October, well into the spring. As melt starts in April, that water starts coming off, peaking in May and June. And so the 3-month period from mid-April to mid-July, which I'm highlighting in green for these 5 years, actually in the early 1950s, it'll be clear why I'm showing you data from 60 years ago. We see relatively low flows and then coming up very quickly during the spring runoff and reaching a peak, dropping back down into the summer and having a fall-winter low. I'm also showing you 5 years to give you a sense of the year-to-year variability, which is pretty considerable on this river. So I'll pass it back to Doug. Oh.
All right. So yeah, thank you. Very nice slides. So if you are an educator, we had the question whether or not these slides would be available, and we are going to post these slides online, and you can both listen to the recording and also use these slides in your classes if you see fit. We haven't had questions on the chat yet, so please feel free to ask. We are here to answer any of these questions. Okay, so our next question is, so when did the water management start? We could see here snowmelt, the hydrology is variable, and it all fluctuates over the years, but when did actually the water management start? And Doug, I think that would be...
Well, one of I guess the first key milestone in the management of the river is 1922, when a compact, an interstate agreement was negotiated. And I know this slide's kind of busy and complicated. The people to blame for that are the people you see in the lower right-hand picture there. Those are the people that negotiated the Colorado River Compact in 1922. And all a compact is an interstate agreement, 7 states in this case, and this is an agreement about how to divide up this river. And essentially what they did, they decided that they would divide up 16.5 million acre feet. That's what that MAF means. And that's probably a unit of measure that many of you have no experience with. It's kind of an odd number that we use out here in the West. But it's pretty simple. If you imagine an acre of land flooded to a depth of 1 foot, that's an acre foot, and that's usually enough water to satisfy a family, 2 families for a year, 2 urban families for a year. So maybe that's a little context. These negotiators decided they would divide up 16.5 million acre feet of water among the 7 states. And they divided those states into 2 groups, the upper basin states, which is Colorado, Wyoming, Utah, New Mexico, and the lower basin states, which is Arizona, Nevada, and California. And basically what they said is that in the compact they said, we'll take 7.5 million acre feet, we'll give that to the upper basin, 7.5 acre feet for the lower basin, and we're going to assume that at some point Congress will allocate some water to Mexico, and Congress eventually did that about 20 years later, and that's where the other 1.5 million acre feet comes into play. So you have 16.5 million acre feet allocated. Also at this time of this compact, the main reason they were doing this is because people in the lower basin, specifically in California, were pretty eager to get development of this river underway. And so at that time, they took that 7.5 they allocated to the lower basin states and fine-tuned it a little bit and said it'll be 4.4 million to California, 2.8 million to Arizona, and 300,000 acre-feet to Nevada. And so the upper basin states didn't deal with their allocation until many years later. And you can see they did that in percentages when they did it later. We'll touch on why they did that because it's very important. But this allocation, the thing to appreciate is the implementation of this is through a formula that says the upper basin states have to allow the lower basin share and Mexico's share to flow downstream each year past the midpoint. And there's this place in Arizona called Lee's Ferry, which is the midpoint between the upper basin states and the lower basin states. And so they have to allow that each year, that water to flow downstream, with the thought that that will end up with about half the water for the lower basin use, about half the water for the upper basin use. To the extent that there's some water that needs to go to the tribes in the region, the thought was that the water would come out of the water the tribes use will come out of the allocation of the state in which the tribe is located. And so that's kind of the framework. There's a lot more details that have been layered on over time, but that was enough to really get things going. And the main thing that allowed to happen was the authorization of Boulder Canyon Dam, which you probably, for those of you who had seen this, you might recognize that as Hoover Dam. It was called Boulder Dam when they authorized it, and by the time it was done, they called it Hoover Dam. Out of respect for Herbert Hoover, who was the person who led the negotiations for the compact. And this is kind of an old picture of Hoover Dam here. If you've been there in the last 2 or 3 years, you'll know there's actually a bridge that goes across or near the dam now, which is a great place to view the dam. But that kind of opened the gates, so to speak, to development throughout the river. And this photo this drawing here is one that I like to use to show that this is one of the most heavily developed rivers you'll ever find. It's an elaborate series of dams and reservoirs and pipelines. Every drop of water is caught by water managers, and it's very impressive, and people throughout the world remark of how impressive it is that they can control every drop of water on this system, and that's done to maximize how many people can be served with this by this river. But the challenge is, or one of the questions is, just exactly how much water is there in the river? I'll let Jeff handle that one.
Right, so returning to this great variability in the runoff, both year to year, also decade to decade, and even century to century. If we look at what the compact negotiators knew about the river in 1922, they had at most 20 odd years of gauged hydrology from which to use as the basis for how much water they would allocate. And at that point, it looked like they had an average of 16 to 17 million acre feet a year coming through at Lee's Ferry, this middle dividing point of the river, to divvy up among the states. So that was the operating assumption. And then the 90 years since then have shown that assumption to be false. The reality is that there's a little less than 15 million acre feet to divvy up. And you can see tremendous variability, both year to year and decade to decade. We can also use tree rings to get a longer view of the past. Before I do that, I should point out this is naturalized stream flow. This is telling us what would be flowing in the river had upstream management and dams not been built. And so if we were showing actually what was gauged at this point, it would be somewhat lower, about 3 million acre feet lower by the present time, reflecting the water that's being used in the upper basin. So here's what the tree ring record shows, and this is a 1,200-year record based on moisture-sensitive trees from around the Colorado River Basin. And what we find is that the early 1900s, so that period on which the 1922 compact was based, is in fact one of the wettest periods of the last 1,200 years. It is completely unrepresentative of the conditions before, or for the most part, since. And so you could say this is the original hydrologic sin of the compact. They assumed more water than actually exists. So with that, I'll return.
Yeah.
Oh, sorry.
Just go back one. So that really nicely summarizes, I guess, the big catch that exists here. And so just thinking as an educator, how do you use this? And there are so many tree ring activities. If you like to do hands-on activities, you could easily do a tree ring activity, have students understand what tree ring dendrochronology is all about, and then tie this nicely in using what we just heard about into policy, water in the West, and make it relevant to people's lives, that why scientists study the past. So this is really a nice way for educators to tie this in both in informal and informal science. I'd like to remind everyone, if you have ever taught about this and you have nice resources, or if you are a scientist and have great data sets available, post it on the chat window. We are monitoring that, and again, post questions if you have any. So before this webinar, we talked, and the first thing, so we asked you guys, what's the story about the Colorado River? And the first thing that you said was the river is in trouble. So can you explain to us why you think the river, or why you say the river is in trouble, and how that?
Sure. We'll give you a few examples of why this river is in trouble, and this is a somewhat complicated slide, so I'll take a couple minutes to get this right here. But this is the hydrologic sin that Jeff mentioned translates to a political nightmare, and let me explain that nightmare a little bit. The pie chart here shows the allocations of the river to the 7 states and to Mexico, based on the assumption of having at least 16.5 million acre feet of water in this river, and you can see in the table that what those numbers what that translates to in terms of an allocation for each state. But you also heard from Jeff that the long-term average of flow in this river is probably closer to 15 million acre feet, which means somebody has to cut back how much they're using. And the logical thought, at least to me, it's the logical thought was, well, okay, we all made a mistake. We overestimated the flow of the river. Let's all cut back 10%. Our allocation's 10% or so, and then we'll be fine. But because the formula for implementing this agreement called upon the upper basin states to release 7.5 million acre feet downstream, and to release that 1.5 million acre feet for Mexico, because that formula was based on the idea that what would be left over would be 7.5 for the upper basin states, but in fact it's not 7.5. And so to the extent that hydrologic sin impacts anyone, it impacts those 4 states upstream. So they all get a little, as a practical matter, they all get a little less than they thought they negotiated. And that's what that little red dotted line in that pie chart means. Those 4 states are going to have to take a little less water than they thought. So that's the political issue. That's the legal issue. Not to suggest there's only one political or legal issue, but that's the heart of most of the angry conversations that take place. But there are some other things going on here as well. Let me talk briefly about the environmental issues. The graph there shows flows of the Colorado River to the Colorado River Delta, and this is the point in Mexico where the river reaches the ocean. And you don't have to be a scientist to understand from that graph that as development happened on this river, the amount of water that made it to the ocean declined over time, such that since the building of Glen Canyon Dam, the river, which is shown in the dotted line there, the river just hasn't made it to the ocean. And that's what the photograph in the background is. That's the end of the mighty Colorado River, many miles away from the ocean. This is a delta that at one point was as rich and vast of wetlands as you'd find anywhere in North America. Now it gets virtually no water. There's some agricultural drainage water that makes its way into the delta. But except for really wet years, and the graph will show you a few really wet years in the early 1980s, except for those periods, no water reaches the ocean. And so that's, in terms of environmental impact, you can imagine that that's pretty devastating. Further upstream on the main stem of the river, you have endangered fish. The 4 ones pictured there are all listed on the Endangered Species Act. These are fish that are, to a lot of water managers, these are a problem only in that it creates limitations on the construction of new projects and some limitations on how water can be managed. But these fish, they really speak to a earlier time in this river's history when the physiology, if I'm using that right, of the river was different, and these fish went from being perfectly adapted to their situation to very poorly adapted to their situation. Let's see.
So,
Jeff, yeah, you want to take that?
Sure. So the declining flows in the very lowest part of the river, and particularly the delta, have obvious implications for life both in the river and alongside it. The implications of our management, not limited to, but certainly including the big dams, the implications for the wildlife and fish, such as these 4 endangered fish. It's a little more subtle perhaps, but we can illustrate it with a few graphs showing changes that have occurred just below Glen Canyon Dam since Lake Powell was filled in the 60s and 70s. And notice the water coming out at the bottom from the power plant once it's spun the turbines and generated electricity, how clear and green that is. So look at that first. And those 4 endangered fish evolved with muddy conditions that helped them evade predators. They were accustomed to being in very muddy water. And after the dam closed in 1963, suddenly the suspended sediment load and the load, what we call the bed load, what was crawling along the bottom of the river, went down by at least 95%. It was being trapped behind Glen Canyon Dam. And so the only sediment now in the Grand Canyon stretch was being contributed by the relatively small tributaries when those would run big after summer thunderstorms and such. But suddenly this water that had been muddy for millions of years is now running clear in the Grand Canyon. It's also much colder than it was, and on average, and going through a much smaller annual temperature range. This used to be a warm water river. Now, that said, it went through large annual fluctuations from nearly freezing, this is at Lee's Ferry below Glen Canyon Dam, up to 85 or 90 degrees in the heart of summer. As soon as the dam started filling in the 70s, that range started to decrease after the dam was full, and the water that's being released from the dam is being pulled out of the depths of the reservoir. That water is now a constant, about 9 to 12 degrees C, so about 50 degrees Fahrenheit. And so that is a temperature that the 4 endangered fish can tolerate, but it's much more favorable for cold water species like the introduced trout that have really come to dominate the stream ecology of the river there. So clear water, cold water, and also the dams have cut the top off of the annual hydrograph, so that really sharp spring peak that we were seeing. If we look at this graph, it's showing the peak flow over time from 1900 on to the present. And the peak flows would range from 50,000 cubic feet per second up to, in the very early part of this period, over 300,000 cubic feet per second. And after Glen Canyon Dam was built and they were regulating the river very strictly for hydropower production, they wanted a constant flow, and so much lower peak flows, averaging about 20 to 25,000 cubic feet per second, with the exception of a few, and you can see after 1963 you have a handful of flows that are quite a bit bigger. A few of those are experimental flood flows that have been released deliberately, both to help the ecology of the river and to help rebuild beaches that the rafters and other recreationists in the Grand Canyon need for camping and that have been progressively lost since Glen Canyon Dam was closed. So there have been several of those. They've been, I think, partial successes in rebuilding the beaches, but those beaches then get eroded away once the flow regime returns to its unnatural state that we have it in now. and the fish are still, not going to see the flows that they had become accustomed to in maintaining the off-channel backwater habitats that they used to spawn in.
Nice. So this really shows there's a lot of stakeholders. There's the fish, there's campers, there's policymakers, there's all the people that depend on the water. So there's lots of people pulling, and here is the Colorado River in trouble. So let's see. One of the questions from the chat was already answered. There's one question that's just being typed out there. How often are large amounts of water released to stimulate floods? Do you want to talk about this, Jeff?
I don't have the number right offhand. I know there was the first one, I believe, was in 1996. I think there have been 1 or 2 experimental flood releases in the mid-2000s. I don't know that there's been one since. So every several years, to the extent that the researchers studying the effects of those believe them to be useful, that will be weighed against the needs of the endangered fish, the needs of recreationists, and of course the desire to keep as much water back in the reservoirs for hydropower production.
Yeah, it's important to appreciate that we're talking about releases from Glen Canyon Dam, and I don't. It's been a while since we showed you the map, but just to orient yourself, Glen Canyon Dam is basically upstream of the Grand Canyon, where Hoover Dam is downstream of the Grand Canyon, and so we're really just talking about this stretch of river through the Grand Canyon. And given that that is a national park, given that it is a very popular recreation area, that's why the thought was, let's do some of these experimental releases and try to get some environmental benefits through that region. But there is not a predictable schedule as to when these releases take place. The parties upstream kind of are protective of that water stored behind Glen Canyon Dam and Lake Powell. They really don't want to see any more go downstream than is absolutely necessary. It disrupts hydropower generation. It disrupts some of the management of the regime. So you get this water users on one side and your environmentalists on the other side with very different ideas as to how often these releases should take place.
Yeah. Thanks. So thinking again as an educator, stepping back, there are really a lot of different hooks that you can use for using this in the classroom or in whatever environment you're doing this. You could go from the life science biology side, you can even go from the recreational side or the water use. You can talk about the 2 big issues, quantity and quality, that were touched on here. And again, there's slides available, we have data, so if you are interested and want to participate in the curriculum development, just contact us and follow the links that we've posted. Please keep asking questions on the chat. As you can see here are the experts that can answer them. If you have resources, please post your resources if you've ever taught about this. So we will. There's just a prompt. We will update the website. The website connections, the resources are going to be linked there on the front page. So we will send a follow-up email and let you know where the resources are located. So is the situation getting better or worse? Is it like you've described the problems, but is it on the uphill? Is it downhill? What would you say?
Good question.
So on the water supply side, the situation has definitely been worse in the last 10 years. So worse, at least in the short term. Since 2000, the average annual flows in the river have been very low. In fact, it's the lowest decade-long period in the last 100 years and one of the lowest in the last 1,000 years. That instead of the 15 million acre feet that we see in the 100-year average, there's been a little over 12 million acre feet available, so about 20% less over the last 14 years. And if we try to parse out why those low flows have occurred, the main cause is that there's been below average precipitation across the basin and in those mountain headwaters supplying the vast majority of the runoff. And this is likely a consequence of natural variability, things like El Nino and La Nina and other longer sort of quasi-cycles in the climate system that influence the Colorado River Basin. But what is almost certainly a contributing factor is the above average temperatures that we've seen in the last 10 years and longer that are likely due to anthropogenic climate change. And so if we look into the future using the global climate models, we find that for this region, for the Colorado River Basin, they're very uncertain. They don't have a strong consensus regarding the change up or down in the future of precipitation. But there is high confidence in future warming, of course, that we see that globally. And so if we look at output from the climate models, temperature, precipitation, run them through a separate hydrologic model that generates simulated runoff for the Colorado River Basin, what they tell us is that decreasing flow is likely for the Colorado River over and through the 21st century. And the red line is showing a median of about 40 different model runs from a middle emission scenario, suggesting that by mid-century, so the 30 years centered around 2050, that we'd see about 13 million acre feet in the river rather than the 15. So conditions over the long run similar to what we've seen in the last 14 years or so. And so that's on the supply side. And then on the demand side,
it's kind of the cruel joke in this basin that is about the time around 2000 that this drought started was also the time that the growth, the steady growth in demands, and demands is code and water language for consumption. Demands caught up with this average supply number, and so you get this point where there's this cushion for all these years between supplies and demands. Right about that time that cushion is used up, is about the year 2000, we hit this drought period, and so very quickly you get to this imbalance between supplies and demands. And what happens on a river when you have this imbalance? Well, the only way you can provide water to your customers, provide water in excess of what Mother Nature is providing, is you have to take it out of storage, out of the reservoirs. And this is a picture of Hoover Dam looking back into Lake Mead. This is the facility near Las Vegas. And you get these bathtub rings, as they're called. As the water levels are dropping, you get these very dramatic white marks on the walls there of the canyon to show where the water level used to be. And so it's a very powerful, very, in many respects, very useful physical feature of the system to show people that there is this growing imbalance between supplies and demands. This is another way to show that imbalance. This is just a projection of, again, supplies and demands that goes up. Left of the dotted line is historical, right of the dotted line is a projection. And you see the projection, as Jeff told you, is for supplies probably to drop a little bit. Well, the projection is also for demands to continue to grow. For a river where supplies and demands are probably not in balance currently, to have supplies continuing to drop while demands continuing to go up, obviously is just not going to work.
Yeah, so there are some questions on the chat. What about diverting water to Front Range cities on the east side of the Colorado River Basin? Any comments?
Well, I showed you the map of all these cities, including the Front Range cities that are outside of the basin that use Colorado River water, and that's really important to appreciate that when you divert water physically out of a basin, in that case from the Colorado Basin to the South Platte Basin, 100% of that is lost to the system. None of that goes back. None of that, to the extent that not all that water is consumed by those Front Range cities, what's left then is put back into a new basin, into the South Platte Basin, and it's actually quite useful to the South Platte Basin. But to the extent that there are diversions to Denver, and to Los Angeles, and to San Diego, and to Albuquerque, and to Salt Lake, none of that water comes back. And so those diversions out of the basin are really a concern, especially those diversions high upstream, such as the ones to the Colorado Front Range, because that means there's just that much less water to flow all the way down the system. So that impacts the environment, that impacts hydropower generation, it impacts recreation. Those diversions are really important.
So yeah, just again thinking as an educator, Jeff brought up this point about change over time, and that this all is happening at there's variation over time, and that's really something that is really hard for students to understand, the concept of geological time periods. And this is really understanding the past and what happened over a long time period is something that can be very well used here to show what has happened here and how variations and changes are influencing policy, essentially. There has been a comment on the chat that it's that looking at the water budget would be a very good learning activity, and that looking at evaporation especially would be very helpful to when talking about these big reservoirs or the diversions to Los Angeles. I think they're open water just flowing through the desert, so there's a huge amount of evaporation. But what's happening to address these issues?
There's several activities underway. I mean, it's very, the problems on the river are certainly have got the attention of political leaders in the region and certainly water managers in the region. And so a lot of things going on. There's been a new agreement in 2007 that among the lower basin states that said, you know, if we ever start running out of water, how are we going to share it amongst ourselves? There's a new agreement with Mexico about, you know, if water supplies get really short, how are we going to share that shortage with Mexico? And there's also been this process called the Basin Study. And there's a little schematic there for you about what was done in this study in terms of looking at supplies, looking at future demands, looking at that imbalance between supplies and demands, and then asking people for suggestions as to how to deal with that imbalance. And there's a range of suggestions and some, you know, and again, get back to this concept of a budget. Some people focus on the supply side and say, oh, you know, there's various ways we can increase the supply in this basin. Some people focus on the demand side and say, you know, the single biggest use of water in this basin is to grow crops that are fed to cattle. People say, you know, before we get ourselves in a real bind here, we need to look at how we're using water. And so some of these issues were addressed in this recent basin study. One of the most interesting things of this basin study, though, is really the first major water management effort in the region where they decided to look at these climate scenarios that Jeff's been talking about.
So, as Doug said, this was kind of a novel thing in the Colorado River Basin, and it's really a leading effort in the country, especially for the Bureau of Reclamation, which co-led the study. The output from global climate models was used to help define one of the four different water supply scenarios that they used. They looked at the gauged stream flow record as though the past would repeat itself. We know that's not likely to happen now. The tree ring reconstructed flows, asking if the droughts of the distant past recurred, what that would do for the system or do to the system, blending those two, and then looking at the projected flows from global climate models. And this was probably unthinkable 10 or 15 years ago that a report or a planning document of this type would include such explicit incorporation of climate change information. And so it's, I think, a very hopeful trend.
In the basin study, again, they asked for suggestions as to how to deal with this problem. And the figure in front of you is just, and I won't try to talk you through it, but it's just gives you a flavor for all these categories. People talked about desalination. They talked about importing water into the Colorado River Basin from other basins. They talked about water conservation. They talked about transferring water from agricultural users to the cities. Then all these options were evaluated in a very general way against criteria such as how much would this cost, is this technically feasible, so on and so forth. And it was a very preliminary effort, but it's led to a few subsequent efforts particularly to look at water conservation and to look at transfers of water from agriculture to the cities. And so there's certainly a lot of interest in finding solutions in this basin, but there's a lot more work to be done.
Yeah, so again, this is the basin study was a big deal for policymakers and scientists to all come together and produce this document. So if you wanted to use that in the classroom, we've posted an executive summary on the web space. So there is this very busy looking diagram on the slide, but it's actually, if you go in, you can see the different scenarios and different solutions. So what you could do in the class, you could assign the different scenarios for different groups, for example, and have them do something like a jigsaw activity, discussing or debating, putting themselves in different policy holders. And so you could use that basin study to really get the students engaged and putting them in the role of politics, for example. So you've both mentioned uncertainty in this. So how would you describe how uncertainty shapes the future of the basin? Jeff, do you want to
Sure.
start?
So we'll talk first about uncertainty in the future water supply. Using the output from the global climate models is that not the only indicator of uncertainty, but the differences among the different model runs are, tell us something important about the unpredictability of the future trajectory of the system. Whether it's the uncertainty related to how on a global scale carbon emissions and other human changes to the climate system will filter through and affect the basin at the regional level. The uncertainty related to natural variability, like we've had in the past. Will we have a 20 or 30 year wet period and coming up soon? We hope so. So there's a lot of uncertainty, and looking at the climate models, you can always look at the average or the median of a bunch of models and say, oh, it's going to go up or down, but there's always a lot of variation within that ensemble or set of model runs. And so for the Colorado, most runs show decreasing flow in the 21st century, but some do show increasing flow. So we need to make sure that our strategies are kind of open to both possibilities, and we know that the high variability we've seen in the last 100 years, the last 1,000 years will continue. We have a little less uncertainty about the timing of runoff. We have the shape of that annual hydrograph, when that peak will be. As warming continues, and we're pretty certain about that over the next century, the snow is going to melt and run off sooner in the spring, and so that peak will start shifting, and that has implications for farmers and others who are pulling water directly from the river. It has implications for the ecosystems, as that peak flow is going to come at a different time of year than everyone is used to.
And let's look at the other side of the water budget and the uncertainty there, the water demand uncertainty. The photo is of the Bellagio Hotel on the Las Vegas Strip, which has these fabulous fountains. And I don't show this to, most people like to point to the Bellagio. Most people that talk about water point to the Bellagio and say, there's an example of wasteful water use. And that's not why I show this picture. In fact, they use very little water at the Bellagio, and it's all recycled several times. The reason I show this picture is that to illustrate that while the climate models are uncertain about how much future supply you can expect, it's also pretty tricky to calculate future demand. And no place illustrates this better than Las Vegas, Nevada. Back when the compact was negotiated in the 20s, Las Vegas was just a tiny little town, and everyone assumed it would stay a tiny little town. You may remember from the allocation, the pie chart I showed earlier, Las Vegas, or the state of Nevada, only requested and only received 300,000 acre feet of water from the river. That's roughly 2%. Why just 2%? Well, they couldn't imagine how they could possibly ever need more than 2%. What in the world in southeastern Nevada was going to use a lot of water? Well, Las Vegas came around. And to put that 300,000 in perspective, one of the questions was about how much water is lost to evaporation. There's roughly 2 million acre feet lost each year to evaporation on this system, probably a little more than that. So, calculating and making plausible estimates of future demands, it's not that easy. And then there's agriculture. This is where most of the water is used. Agricultural water use can go up sharply or down sharply based on a lot of factors. As Jeff mentioned, if the melt is earlier, the growing season becomes longer, that can really spike agricultural water demands. If market conditions are negative for farmers, maybe that drops water demand. A change in technology, maybe from flood irrigation to the sprinkler irrigation you see in the photo, that can shift agricultural water demands. There's a lot of uncertainties there. And finally, energy. We haven't talked at all about energy development. Energy development uses a lot of water, and there's a lot of energy development already in the southwestern U.S., and there's a lot more proposed. And some of the technologies, such as oil shale development in western Colorado, should it ever emerge, it's one of these things people say it's the next big thing, and it always will be because it never seems to happen, this oil shale industry. But should it happen, something like that could dramatically increase water demands for the energy sector. So there's all these uncertainties on the demand side. So you got a lot of things changing at once, and that's kind of the problem here, is that how do you deal with 5 or 6 things changing at once?
And the model for planning and management on the river, and really for rivers across the U.S. and the world, has always been kind of single target planning. You have you've got 16.5 million acre feet. You think you're going to divvy it up among these uses, and you expect the same strategy to work year after year after year. And if we're heading into an increasingly uncertain future with respect to both supply and demand, how do we set targets? What is our framework? And if I can divert you away from the cartoon for a bit, on the upper
it's a good cartoon.
Right, that cone is what's been called the cone of uncertainty for the people who have been developing what's called scenario planning, which is, on the left side of the cone is where you are now, and then recognizing that there are a number of future possibilities that kind of expand outward from that point, depending on the different conditions of supply and demand and we've talked about. You would try to develop several scenarios kind of out there on the end of that cone that seem plausible and reasonable, and then think about the different management trajectories that would get you there and the decision points you would have to make, and make sure that if you make decisions at those points, that you don't foreclose opportunities to reach those points that are further out on the cone. So that's one way that water, at least some water managers, municipalities are kind of now approaching their planning challenges is by thinking about multiple futures, and that type of scenario planning was also encoded, as we heard, in the Colorado River Basin study that came out a year and a half ago.
The Basin study was one of the first recognitions that there are several things changing at once. And if there are several things changing at once, we're going to have to do our planning exercises different. We're going to have to think about risks different. We're going to have to think about scenarios differently. So everyone's still on the steep part of the learning curve and trying to figure out how do you plan for water resources in this new era.
Mm-hmm. Yeah, so I framed this question as uncertainties, and just stepping back, because there is a difference between uncertainty when scientists talk about this, and then there's something that is an everyday idea what uncertainty is. So if you talk to your students in the class about there's uncertainty in the future, that is the everyday first thought is, they don't know, which is not true. And I hope you've seen this in what was described, that there is error to it, and it's unclear what's going to happen, but it's an informed error. It's not an uninformed error is there. So it's really important to clarify this word, and sometimes it's really when we scientists talk, we use these words that mean something to us, but it doesn't mean something to someone else. I mean, theory is one of these other examples. If somebody has a theory, that's a pretty big deal in science, but it's not a pretty big deal if my daughter tells me she has a theory about when she's going to get dessert. So we have posted on the website a resource about uncertainty and myth in science and communication. So if you want to check out the website and learn more about this, how you can use that also as a talking point in your classroom to learn how to read science better and the scientific reading skills in students, that's a good place to do this. So we've talked a lot about problems, about uncertainty, about questions. What are solutions? How can teachers and kids, citizens, all of us, how can we see the future? How can we help bring a positive future? Do you want to comment on that?
I'll take the first stab at that, acknowledging that that's the difficult of all these questions you've had. This is a difficult one. I guess that's the nature of life. It's usually easier to identify and talk about problems than to identify solutions, and where different people fit in on these solutions. But so I'll say a few general things, and Jeff has a few as well. But I'd start with this idea of conveying to your students to think about water resources management in terms of trade-offs. We're talking about a finite resource, and so if we need more water for cities, that means there's going to be less for farms or less for the environment, or so what's the proper ratio here? I think I mentioned that agriculture uses the majority of water in this basin, but most of the economic activity is generated in the cities. Well, is that a compelling argument for moving water from agriculture to the cities? If you move water from agriculture to the cities, then you have whole large rural areas that lose their only economic engine. Is that what we want? Do we want to discourage energy development if it requires the use of water? Well, people will say, no, we need to encourage energy development because it provides national energy security, or there's other considerations here larger than water. So I guess, that's the sort of very practical discussion I think that needs to happen, is what vision do we have? What future do we really want? There's a few obvious things as to what we do is just to the extent that you can use less water in any sector, that strikes me as a smart move. Most people think of water conservation as strictly an urban activity, and the cities certainly have a role in this, but there's a lot of potential on farms as well. The figures, the slides there is of urban water conservation. I think it's important for people to appreciate that many of these southwestern cities, the cities along Colorado's Front Range, most of the cities of Southern California, many of the Arizona cities, many of these cities, we're using more water in our cities on our lawns than we are in our homes. If you really want to talk about water conservation, you need to talk about what the landscape looks like outside your home. So there's, another thing to think about. So there's, it's clear that there's some trade-offs. It's clear that we need to think about a vision for what we want the Southwest to look like. And some of the solutions, such as conservation, are obvious. But there's a lot of thinking and a lot of work that needs to go on here.
And returning to the notion of change, I think we all have to recognize that change is always going on in human and natural systems. That said, in the 21st century on the Colorado River, we see that the pace of change, possibly in the amount of water that's available, will change faster than it did in the 20th century or in centuries prior. I think we focus a lot on the challenge for planning and management. We could also see it as an opportunity to change our practices that probably weren't going to work even if the conditions of the 20th century had continued on. Something would have happened, just the natural variability, the changes in population. So this is an opportunity now to do things differently. Now that we see some things coming in our, in the tools that we have to kind of assess the future as well as we can, we can do things differently, perhaps. The things that seem to work well in the 20th century are not necessarily what's going to work so well in the 21st century. The main, you could say, management tool in the 20th century was building dams and creating large storage reservoirs, and that solved a lot of the most pressing problems that we had on the time. How to control flooding, which was really serious in the lower part of the river and prevented development and population in Arizona and California in the lower basin. It also solved the problem of drought management and mitigation. By having this large supply of water, you could get the system and its uses through these lean years with a enormous storage capacity. 4 times the average annual flow is stored in the reservoirs on the main stem. But this particular solution may not work in the 21st century, especially if the runoff does go down during that time period, and we would have to look at some other solutions for our problems, and we conceive the problems differently.
Mm-hmm. So it is a complicated era, but I guess I'm going to come back and say the problems are very simple, disguised with all sorts of complicated details that I'm afraid we filled your head with here. But the slide here I think is supposed to represent different sectors competing for water. Maybe for the purpose of this point, and that's part of the challenge, but let's also think of the different states competing for water. Again, I've pointed out this issue that the river is over-allocated, and everyone thinks that shortage should be dealt with by the other guy and not by them. And so there's this, I think it's a very basic problem that we've all run into, of what do you do when there's not enough, or it's not as much to go around as you originally thought there was, and so the states, through their politics and through their lawyers and through the political posturing, are really, what they're doing is trying to have a very simple conversation, I would say. And they're trying to say, how do we share a limited resource? How do we make those decisions? If someone's going to be cut back, how do we make those decisions? How can we trust everyone to play fairly? That's one of the problems in this basin, is that the state of California has more congressional representatives than the other 6 states combined. So people in those other 6 states say, we can't sit down with California and talk about this because they'll just steamroll us in Congress. There's this fear. How can everyone equally share the risks? Jeff talks about climate change. We might see a significant decline in the amount of water that's in this basin. How do we distribute those risks in a way that people think are fair? And finally, this question of, are we at that point where doing nothing is riskier than doing something in terms of this allocation issue? I think that people have finally decided that we need to do something, but what it is, not entirely sure. So we need some new thinking. And
the one way that people, no matter what river basin you're in, can help the Colorado River and the rivers wherever you are, is by becoming more informed about water issues generally, about the water issues in your basin. Where does the water come from? Where is it going? Who's using it? What are the conflicts? What are happening to the ecosystems because of that water use? What are the prospects for the future? And there are many more opportunities for public input onto the types of processes that Doug was talking about than there were 20 or 30 years ago. I mean, the basin study, you had multiple public comment periods for drafts of the report. The Bureau of Reclamation has encouraged any and all citizens and citizen groups to make themselves available so that they can be part of follow-up activities for the basin study. Water providers, your city, your irrigation district where you live, if you're an informed person and understand the issues around the river basin you live in, they are, having worked with water managers for a while now, they're eager to talk to people who understand the system and have questions and concerns.
Yeah. Well, thank you very much. So I think it's a nice way to finish this, talking about solutions, that anyone who's talking about climate change, teaching about climate change, thinking or worrying about climate change, it's worrisome and it's daunting to students, and really if you only paste this dark picture what's going to happen in the future, maybe like this slide here, with the dark clouds over the Colorado, that can really turn students off thinking and wanting to be positively engaged. So I think it's good to point out all these issues, but it's really been also a best practice to weave in the solutions. What can we do? Just empower your students to do something about it, or be engaged in some ways, and that is going to get their attention a lot more than just talking about the terrible scenarios that might happen and kind of putting our head in the sand. There have been a few questions. Comment earlier on the amount of evaporation that is happening on the reservoirs. Maybe, Doug, do you want to comment on where,
we
or
covered
one
that
of
a little
you?
bit.
Yeah, I think he answered that sort of in line.
You
might say.
said, but where is that? Is that on the big
Most
reservoirs?
Most
Is that on
of
the?
most of it's from Lake Mead, which is again the facility behind Hoover Dam by Las Vegas, where I showed you the bathtub rings. Most of it's there. Lake Powell, further upstream, has quite a bit of evaporation, but it's at higher elevation. It's a little cooler and a little less evaporation. But the lower third of the river is just a series of reservoirs, basically, and that's the driest and hottest part of the basin. So there's a lot of evaporation there as well. And in the upper third of the basin is probably where the evaporation is least, but still you have a lot of smaller facilities, and you know it adds up. It adds up, and it's one of these ironies of you're in an arid land. You want to store as much water as you can, but at some point it's counterproductive. At some point you have so much water stored in these reservoirs that as they get fuller, they spread out more, and there's more surface area, and the evaporation keeps going up and up.
So another question here: which energy development methods are most
Sure.
water intensive?
You know, it's so there's energy development has many stages to it. You know, there's the actual if we're talking coal, for example, it's the dragging of taking the coal out of the ground, but there's also then the water that's required in the power plants where you burn that coal, and so coal, particularly the burning of the coal, is an example of a power generation method that uses a lot of water. Nuclear is seems to be on its last legs in this country, and maybe for several good reasons, but one of which is that it uses a lot of water. The natural gas development that is occurring throughout the country, some of that uses a lot of water, some of it generates water. Some of that natural gas development requires taking water from deep underground, water that otherwise wouldn't have ever been tapped, and bringing it to the surface and putting it into the streams. And so that's very much case specific whether or not that's friendly to the water resource or not. But what you see is that as the energy system in this country transforms, the directions that are most climate friendly are also most water friendly. For example, generating energy through windmills, very climate friendly, no greenhouse gas emissions, doesn't use any water. Generating energy through photovoltaic cells, solar cells, again, there's a little water involved in the production of that equipment, but it's very little, and it's water friendly, it's climate friendly. And so the trends in energy development by and large are positive. They're energy friendly. But some of I think I mentioned oil shale. There are some ideas out there that aren't so water friendly. Oil shales deposits in western Colorado, for example, that people want to develop, we require a lot of water. So part of it is site specific, but you know, the solutions that are water friendly tend to be the ones that are climate friendly, and so this is one of the notes of optimism. Can I squeeze a note of optimism here in a pile of doom and gloom? I think that's one of the more optimistic things going on in this basin.
Okay. So there were a couple of comments on the chat about how to engage students that are outside the basin. Sure. Do you have suggestions?
Well, of course, those of us who live, very close to the Colorado River Basin, use water from the basin, think it is the most interesting river basin in the U.S., if not the world. Not everyone may feel the same way, but it's a very visually charismatic river, going from these high mountains, through the Grand Canyon down to the arid deserts. Very interesting native fishes in the river. And many people from outside of the basin have visited, one of the national parks in Utah, Canyonlands, Arches, Grand Canyon, so forth, or at least have seen photos, are familiar with some of the outstanding landforms and features of the basin. So that might be a kind of a handle to get people interested in this. Oh yeah, there's this lifeline that's flowing through this amazing landscape, and 40 million people depend on it, including some big cities. About 15% of the country's population depends on the Colorado River just through municipal use, and maybe a larger number through the agriculture. Where does your salad come from? Probably the Imperial Valley. If it's in midwinter, it's coming from Colorado River water. You're basically in your salad eating Colorado River water in the winter.
And there's a lot of issues here in the Colorado that apply elsewhere. For example, this issue of states competing for a limited resource. I mean, I've been asked to go all over the world to help places where they have these interstate disputes. I worked with Georgia and Alabama and Florida and the southeastern disputes down there. North Carolina and South Carolina had a dispute that I worked with them. I worked in China with the government there where there's these disputes about water sharing between different regions of China. Everyone around the world is interested in this issue of as water supplies get tight, how do these different political jurisdictions, how should they interact with each other? And often the message I have for them is, well, don't do what they do in the Colorado River. You can do better than that if you think ahead a little bit and plan ahead. So there's some transferable lessons there. I guess I'd also say that people tend to think of environmental issues as pollution issues or externality issues. My factory pollutes your resource and that sort of thing. But this is, I think, a really good example of a class of environmental issues of we're just dealing with a finite resource, and it's a question of scarcity and exhausting a resource. And in that sense, there's similarities to some forest management issues and to some range management issues and to some fishing and overfishing issues. And so I think, you can put this in a larger context to show students that this is one class of environmental conflict that's, where you can pull lessons out that apply elsewhere.
And just an idea for anyone who's taking this for credit, this would be, you've heard examples from the salad to talking about something that's close to your home and do a comparison. So there is a lot of potential there for curriculum projects. So if you wanted to take this for credit, you can take that on as one of your curriculum projects. So if you have other questions, please post them on the chat. We still have a few minutes here for questions. I do have a question that's probably very simple, but something that came to my mind right away when I started reading about this. So obviously the water allotment was done in a volume of water. So, and can that be just transferred, and just probably in parentheses, to a percentage and just say, well, we've done a miscalculation in the beginning, and here's the assignment. Why would that not be transferred into percentages? But I don't know. There might be a simple question to answer to that.
The hindsight's a wonderful thing, and there's a lot of hindsight on this river. There are at least, I believe there's 24, and that I might be off by one or two, but about 24 interstate water allocation compacts in the U.S. So 24 agreements between states to divide up the flow of water. And the Colorado River Compact was the first of the 24. And so there was a lot of learning that took place after the Colorado River Compact. And so in almost all those other compacts, they use percentages. Mm-hmm. And when the states of the upper basin in Colorado decided amongst themselves how to allocate water, you'll notice they use percentages because they already learned that this idea of absolute volumes can get you in trouble. And so, there's several mistakes that were made in that first compact that we've learned from. That's an obvious one. Another one that I'd say we haven't learned from is this idea that the compact did not reserve a drop of water for the environment. And so in other places in the world that have dealt with similar issues, some places have said, we should take the first, 20%, 30%, whatever seems appropriate in that region, and say that amount of water is reserved for the environment. The rest, then we can divide up among water users for their consumption. That's another thing we've learned from this compact. Some of the other things is that the compact allocates surface water, but doesn't talk about groundwater. But groundwater and surface water are connected. You pump enough groundwater, you essentially drain a river from underneath. There's been a lot of conflicts with compacts about people say, oh, we're honoring the allocation of surface water, but by virtue of their groundwater use, they're violating the agreement. So yeah, there's a lot of learning that goes on, but I guess the heart of your question is, once you've learned that, how can you go back and fix an agreement? That's really tough. You can either negotiate a fix, and the problem with negotiating a fix is that for a compact to take effect, all the parties, all the states have to agree to the exact same language, and they can revise it by all agreeing to new language, but whatever mistake has been made, has to benefit someone at the expense of someone else. And so you'll never get this situation where everyone sees a benefit to renegotiation. So it's really hard to get a renegotiated agreement. And then the only option after that really is to take it to the Supreme Court. If states have a dispute against each other, it jumps right to the Supreme Court. And you can take these water disputes to the Supreme Court. The problem with doing that is you have no idea what the court's going to say. And if the court comes up with an agreement you don't like, there's nowhere to appeal it to. So everyone's afraid of going to the Supreme Court. Not everyone wants to negotiate, but yet everyone realizes that the current agreement has some problems to it.
And I think there was a follow-up question on your comment that the environment didn't get a single drop of water.
No.
Is there any way of tracking that back and saying, fighting this compact on the behalf of the environment?
Not as a whole, not the compact as a whole, but you can go into a particular state and a particular, let's say, national park or wildlife refuge within a state where maybe there's a issue that's related to low flows, and you might be able to force a change in management at that particular spot, and that, might have the effect of somewhat changing the allocation, but it's working, nibbling around at the edges rather than changing the overall structure of the agreement. Because the compact, after all the states agree to it, it goes to Congress, and Congress ratifies it. It's federal law. So Congress has given their blessing to this agreement that did not reserve water for the environment.
Any other comments from the presenters here?
Not really.
No. Okay.
We're commented out.
So in general, it's great that you're all participating. You have this interest and want to learn more. Education is really one of the positive ways of making change in people's mind, future citizens, and having them learn about it, and strengthening the knowledge about environmental issues. And there is no assignment for the environment if in the future it ever comes to renegotiating any compact or that might change if people are more willing to allocate water to the environment. So it's really in educators' hands to do something about this, among other people. So we are almost to the end of this webinar. We have a website that we've shared with you, and we'll share in a follow-up email where we are posting additional resources, where you have a chance to post any resources that you know about, you've used, just as a place to combine all our knowledge of all the people that are listening to this. I would like to thank our two presenters here to coming and present this in such a very easy, digestible way, and with all the nice slides that they've agreed to for anyone to use in their classes. I think I haven't said this in the beginning. Deb Morrison and I are co-facilitating this, and we really try to bring my background is in science. I'm a climate scientist. Deb is an educator, so we are trying to bring together these the knowledge of both of these fields, and we are really hoping that in the follow-up to all of these webinars, we'll be able to work these two domains together and really have the education benefit from the science, and ultimately the science benefit from the education, because that's where funding and support comes from. We have another webinar coming up in about a month, November 13th. We're going to be talking about the Colorado flood here. We have a panel of 3 experts that are going to be presenting initial results on what happened here in Colorado and how to tie this in a bigger picture. So we'll be sending out emails to all of you about time and sign up and things like that. Feel free to email the facilitators at the email we are providing here, or the scientists if you have any questions directly. They've given their emails, and we're going to post the slides on the website. We'll also have, as I said earlier, the talk over the slides, so you're going to have the broadcast available to you if you want to use chunks of this in your classroom where you have real scientists speak in the class, or want to repurpose it in any other way. That's possible too. All right. I don't think there are any other questions from the chat for now, so thanks everyone for taking the time out of your Wednesday evening. Thanks again to the presenters here.
Thank you.
And the technical people in the background, and we hope to see you all in November.